gone.
It's just paid.
I know it says paid, but I think it's gone.
Why does it say paid?
I'm not sure. Gone? Oh, yeah.
Okay, we're gonna get going. Sorry, a little bit of delay here. So we're doing the method of joints today. I know you're all thinking something that you shouldn't be thinking. And so this takes us to chapter 6, which is structural analysis. This is the kind of stuff, if you know Matthew Kyler, this is kind of the stuff he does all the time. He's a structural engineer. He's what? And then this is the basis of your final project. If you want to do that optional final project, which is really fun, I think you all should do that. So we're going to start with an overview of what trusses are, looking at the method of joints, what these zero force members are, and then we'll be looking at the method of sections tomorrow or tonight. Sound good tonight? Online tonight?
Yeah.
You guys all got time? David, yeah? Okay. Isaac, yeah?
Yes.
Okay. So trusses are these special structures that consist of members that are straight, slender, so you can ignore their own weight because they hold a much larger load than their own weight. And they're pin connected at their ends or approximated by like a gusset plate, which was on the test. That gusset plate, remember that thing we did on the test? It's a plate that you bolt a bunch of members to. And it's because the members are so long, I mean, this would have a moment reaction, but it's not going to be a very strong moment reaction because it doesn't have much, moment arm. So it sort of acts like a pin. But you'll also be able to do that. You can actually, when you do your bridges, you can make gusset plates like out of balsa wood and glue your members together, with these little slender, oval shaped or square shaped pieces of wood. Not really thin. I don't mean slender. I just mean thin. A little thin piece of wood like that will make a gusset plate. That's what you would use to construct your bridge. Anyway, they use them in roofs. They use them on bridges. The thing about the other important thing to define a truss is that the loads on the truss are only applied at the joints. So if you have like a roof built with a truss, they have like a purlin, which is this point here where the roof sheathing is loaded onto, so that it's actually, that load is only being applied at the particular joints here, here, and here. In between is actually not even touching, it's not even touching those members. So, and then also like for the roadbed of a truss bridge, they build these, the deck of the bridge is built on top of these floor beams that kind of go across, start the pins where the joints are, and then these stringers that go along that way. So all of the load of the bridge is applied straight to those, only to those joints. So, so what that means is that simplifies the analysis. Because when you have everything, all the loads being applied to the joints, then all of the members are two-force bodies. And that means the force is acting along the axis of the member. that means each member is either going to be stretched or squeezed. And not bending, because bending turns into, as long as you're not putting a side load on the thing, it will actually be pretty strong under compression. It's very strong. The members are very strong always under tension, because that's just stretching stuff out, right? Compression, they're strong, but not as strong because they will buckle. But if you have a side load acting on a member that's being compressed or stretched, it'll be much weaker. Oh, darn, I got them wrong. I haven't been lecturing in a while, so I forgot. I got to get the unmarked slide. So is this on your handout? So we're going to do some free body diagrams to kind of just show you how you break apart a truss and analyze it. And what you do is you, and this is for joints and members. We're just going to do everything now, and then we'll look at the method of joints. So what we can do is we can apply our whole free body diagram analysis to all the different parts of that bridge if you explode everything. What happens is we can start with, well, let's just start anywhere. Let's just start here with this member AB. Now, why am I on laser pointer and the pen is deactivated? Because I did not enable editing. And I also have to enable content. All right. So we start with member AB. And that vertical member AB is going to have a force acting on it. It's either going to be in tension or compression. But for simplicity, we can just assume all the forces are in tension. And that means the force is trying to stretch out the member. So it's a two-force member. It's being stretched, and therefore it is, the arrows are pulling away from it, right? So, yeah, I guess we're idealizing it a little bit more as we go. This is actually, we're sort of cutting away, you know, this piece right here and kind of showing that thing, right? And then suppose we actually look at like this part here, and you can say, well, okay, if you cut it, you know, if you cut the thing right there, you're going to have a, you know, part of a joint there. And if, again, if these things are under tension, you're going to have these forces, again, pulling on the members. So this FBA here is going to be the same as this FBA here, right? And this FBC is going to be pulling that pin towards it. And then you're going to also have this sort of 500 Newton force acting at that point B as well, right? Likewise, down at A, you're going to have a this pin here where you've got a whole bunch of stuff going on here. You've got, here we are at A. You've got an AY reaction, and oh, by the way, sorry about this. You sort of start doing the whole analysis on the body as a whole. So you look at what kind of reactions is this pin at A going to provide on that structure as a whole? What kind of reactions does the pin provide? What kind of reactions does a pin provide on a body? What kind of movement does it inhibit? Does it allow the thing to translate left and right? Is that pin going to allow that point A to slide left and right? Is it going to allow it to slide up and down? Okay, so those are reaction forces that are going to prevent those motions, right? Yeah, so you'll have an AY, and you can think about, you know, what kind of moment is this 500 Newton force applying, say, about C? It's 500 Newton force. What's it trying to do as far as rotation about C? Trying to make it kind of spin that way, right? So most likely, and you don't have to try to predict this, but most likely AY is going to be pointing down, because that's going to give you a counter moment to try to spin it the other way, right? And those have to balance up. You have to analyze these forces on the body, the external reactions on the body as a whole. Also, because you've got a 500 Newton force pointing to the left, you can probably be pretty sure that AX from the pin is going to be pulling that structure to the left as well. And then the rocker is going to be doing what? Rockers can provide what kind of forces? Remember what a rocker is? We didn't even talk about a rocker. Rocker's kind of like a roller, but it just sort of tilts. It's like a little tilty thing, right? So is that going to prevent a left and right motion? No, can't, right? It's just going to roll. It's going to, tip. Is it going to prevent an upward motion? No. It could, the rocker could conceivably, it doesn't look like it's being attached to the ground. If you look at what the rocker looks like, it's actually just a support. So the only thing it can provide is a normal force going up. And so we would have a CY here. And that CY is going to balance out the AY so that those things add up to 0. And the moments all have to add up at any point on this external structure as a whole, right? And so we solve for these reactions initially without worrying about breaking apart the structure. And then once we have those reactions, we can break apart the structure. And again, we would apply these reactions we just found at A, the AY and the AX here. Pulling at that pin at A. And then this FAB pulling down on this member is going to be pulling up on that little section. And then you're going to also have an FAC here pulling that thing to the right. Well, that's the idea of, how the forces are acting inside this structure. Does that make sense? That if this thing is being stretched, you're going to be stretching these things, the forces are going to be sort of extending them. Question? Yep.
So you said that the 500 force is going to be feeling like counterclockwise. You said we could predict it, right?
Well, the 500 force is going to cause, it's going to want to make a tendency for this whole structure to rotate, say, about point C, right, in a clockwise direction.
And so for this, the pin A, so that it could counter.
Well, one thing pin A is going to have to do is counter that to keep it from rotating, to rotate that way. It's going to,
So shouldn't AY then be up?
how would that keep it from rotating clockwise? If AY is pointing up, isn't that going to cause that thing to also rotate clockwise?
Because the way I see it, it's going down. It's going to be clockwise, right? So then if it's up, it's going to be
Okay, I'm holding a notebook, right? There's a force in this notebook pulling it to your right, right? Right? And suppose I plant this notebook right here, right? Can you see this? I'll put it right here, okay? Pulling this thing to the right. How am I going to keep that notebook from tipping to the right? By pushing up on the right? Is that going to keep it from tipping? No, I'm going to have to pull down on it, right? So that those things keep it from rotating, right? It's just visualizing this stuff. How's it going to move with this force? It's really easy once you can visualize it that way. Don't think conceptually about it. Think visually. So this is just sort of a transition to the more idealized way of representing this thing, which is, let's look at that member as a whole and think about what the pin is doing, and just ignore these little jags coming off of my stupid pen, please. Just do another one for me, why not? Okay. And these forces are going to be stretching that member at the pin. It's a little more convenient to think about the pin itself as a separate member and what that pin is feeling. If FBA is getting stretched that way, the pin is going to be feeling FBA pointing down, right? Does that make sense? again, I'll have a live demonstration come up here if anybody wants to come up here, and I can show you what that means. Or I can demonstrate it right now with my hand. So my finger is a pin, right? My arm, my hand is wrapping around my finger, so my arm is like a member, right? And if my arm is feeling stretched, which direction is the force that my finger is feeling? Up or down? Feeling down, right? If my arm is getting stretched right now, my finger is feeling a downward force. This is really important to be able to see that, right? You see that? Yeah, I look puzzled. Jose, what do you think? You want to come up here? Alvarez, you just came in. I'll demonstrate on him. So we're demonstrating what the effect of a force is inside a structure. And what I want you to do is hold out your index finger, right? Point it to them. Yep. And I'm going to hold it. My arm is a member. My arm is at member FBA, and I want you to stretch my arm out. Okay. Now, what kind of force is your finger feeling, up or down?
Down.
Your finger's feeling a downward. He said it, right? His finger's feeling a downward force. You can all convince yourself, right? Okay. So that's why. I know people get a little confused about this the first time, and I see some blank stares, but I think you get it, right? So so FBA is feeling a downward force, and FBC, if we think of this member BC, which is tilted at a 45-degree angle, also being stretched by its own force FBC and FCB, then the pin here is going to be feeling a sense of wanting to go down and to the right, right? If FBC is being stretched that way, the pin is going to be doing the opposite. It's going to feel the opposite to provide that stretch, right? That's sort of like Newton's second law, the equal and opposite thing, I think, right? And then that pin is also going to be, because all the loads are applied to the pins, that pin is going to also be feeling that 500 Newton force. Okay, and then at point C, which is going to be, showing the equal and opposite again, that point C, if member BC is being stretched, then FCB is trying to be pulled up and to the left. And we've got that CY reaction being applied there, and we've also got an FCA. And this is why I actually don't mind not lecturing, because this thing is just always driving me crazy. And then FCA and FCA going this way. Now, one more thing is the pin at A. The pin at A is going to actually have four forces acting on it. It's going to have AX and AY from the support of that pin there. And it's going to have FAC pulling it back the other way, and FAB pulling it up. And I guess this should be, it doesn't matter if you call it FAC or FCA, it means the same thing. Oh, there is it? Yeah, good question. How many unknowns do you have in this structure? Well, if you count all the different combinations of letters, like FBA is the same as FAB, it's the same thing. We've got an FBA, so the unknowns are FBA or FAB. We've got an FBC, right? We've got an FAC, and we've got what else? AX, AY, and AC. You're gonna find these first. AX, AY, and CY. Sorry. Yeah, it's about 6 unknowns in this one. This is a really simple truss. every time you have a truss, every member has an unknown force inside it. And by the way, so we're drawing the free body diagrams as if the forces on them are all in tension, just to make it easy to analyze. We're going to have, just do all tension, tension, tension everywhere. It's not going to work out to be tension, but when you find the final answer, if your final answer is positive, that means it was a tension force. If you find out that the force is negative and you drew the diagram where it's in tension, then that means it's a compressive force. It's actually trying to squeeze the thing.
And if it's being squeezed, then the tension at the point would be
Pointing like towards it, yeah. Mm-hmm. Good, and all this is set up. This is the preliminary concepts for how the method of joints works. Method of joints says we're just going to look at the diagrams of the joints. Forget the members, because the pins have all the information we need. The pins have all those forces acting on them as well, as you saw, right? Each joint becomes a particle, like chapter 3, a concurrent force system. Remember those particles like knots with cables on them? It's just like one of those things. Those are really easy for us to analyze because they're really simple problems. And what we have to do is first find the reactions at the supports, treating the body as an entire whole, like a chapter 5 problem. And then we go through and do the diagrams of all the successive joints. And it's a concurrent force system, which means there's only 2 equilibrium equations. The sum of the fx's is equal 0, and the sum of the fy's equals 0. And we can look for, question? No, these are 2-dimensional problems, yeah. It's a flat planar, truss is a flat structure, so you can analyze it using 2-dimensional techniques, yeah. And when you start the analysis, you can look for a happy joint, which is where there's only 2 unknowns applied, because you can solve for 2 unknowns in a system of equations in 2 dimensions. You can only solve for 2 unknowns in 2 dimensions. Well, with concurrent forces in 2 dimensions. Complicated. You have to just do it. So here we go. Example 1. Here is the recommended approach. Now, there's a few more elements here, but we start the analysis by finding the reaction at the support. And this is where you forget all the members, you forget all the pins. You're just looking at this whole thing like it's a big, rigid body. And you're looking at what kind of reactions are we going to get at C, what kind of reactions are we going to get at A. We talked about A being a rocker, which is kind of just like a roller. It's not going to prevent horizontal motion, so it's going to have an AY. CY and CX. Now again, if you're clever, you can try to guess the direction of these things. I'm going to follow the lead of the solutions here and draw CX going to the left. How do I know CX is going to the left? It's a guess. And if you want to guess that it's going up, that's perfectly fine. You don't have to worry about the direction of those arrows. You can just draw them going up. If you get a negative number, it means it was going down. When you get good at this, you can kind of intuit that, this is probably going to be going this way, so I'll just draw it that way, and then you're going to get a positive number, and you're going to be satisfied that you guessed correctly. But initially, it doesn't matter which way you guess. For the reactions, just put them any way you want, and just keep track of how they actually work out. So we write the sum of the fx's to do the reactions at the support. This is a problem that involves moments. When you're looking at the structure as a whole, as a rigid body, this is a chapter 5 problem where you got to do the moments have to add up to 0 as well to get those external reactions. All right, so we got the sum of the fx's is 0 on the whole body, right? And look at you can just sort of forget about all the stuff inside it, right? You're just looking at those forces acting on that whole body. Sum of the fx's is going to be 600 newtons going to the right, right? Minus cx going to the left, right? And so that equals 600 newtons. That means, oops, that equals 0. That means, that means that cx equals 600 newtons. Do the same thing for the Fy's. You're going to have an AY, a minus CY, and a minus 400. And we can't solve that because there's two unknowns, right? But we can do one more equation, which is going to be a moment equation. And we can pick any point on that structure. But if we pick a point where there's like two unknowns, we can get rid of those. So we can do the moment, say at C, and then we don't have to worry about CX or CY. So that's going to be, the moments about C is going to be 400. That 400 Newton downward force has a moment arm of what? 3. And you got AY is going to have a moment arm of what? 6. Now, signs, okay, which one is positive? Is the 400 Newton force causing a positive rotation or a negative rotation? Yeah, it's positive. What about the AY times 6? Is that a positive or negative rotation? Clockwise or counterclockwise? Negative, right? So it's minus AY. And there's another force giving us a moment. There's a 600 Newton. What's the moment arm of the 600 Newton force?
4.
Good. Positive or negative? Positive. Causing a counterclockwise rotation, right? Okay, that is one unknown, AY. So this tells us that AY is going to equal, if you do the calculations, AY is going to be 600 newtons. And that allows us to figure out that CY is going to also equal, well, CY is going to equal 200 newtons. The fact that they're all positive means that our initial guess of the direction of those arrows is correct, meaning that CY is really pointing down. It's a downward force of 200 newtons, because that's the way we drew the arrow. Got it? CX positive, meaning the force is going to the left. Let's see. Okay, so that's the reaction to the force. Now the next part is we solve for the member forces. And this is where we can do these diagrams of each pin. Okay. So we've got at C, you know, we've got our reaction forces already figured out, CX and CY. And then we're going to assume all the forces are in tension, meaning a tension force for member BC is going to be pulling the pin at C to the left. Do you agree? If we're stretching out member FBC, there's a leftward force the pin's going to be feeling to the right. And we're stretching out member CD, there's going to be a downward force. Basically, all the forces in tension are moving away from the pin. So we've got an FAB and an FAD and an AY. And there is also a 3, 4, 5 relationship in this angle here. And at D, we're going to have FCD and FBD, also that 3, 4, 5 triangle. And then we're going to have an FAD. And at B, we're going to have an FAB and an FBD and an FBC. So each one of those pins is a concurrent force system, like a chapter 3 problem. We're just going to solve those fx's and fy's. You don't worry about moments because the pin's not going to have any moment, not going to prevent any moments, right? If those members want to rotate, the pin's going to say, go right ahead, right? The thing that's keeping them from rotating are the other members in the structure. So we just have to write the sum of the fx's and the sum of the fy's. And for pin C, it's basically that FBC sum of the fx, sorry, I'm going to write this a little bit better. Sum of the fx implies that FBC equals minus CX. Whatever CX is, FBC is the opposite, right? That's kind of a slam dunk. That's a really easy problem, right? So that means FBC equals minus 600 newtons, which means it's negative, meaning that it's what? Is it in tension? It's being compressed. It's being squeezed. So you can put a little C after it. That means compression. When you're doing your bridge analysis, if you do the final project, the limit of compressive forces is different than tension forces. So you got to know if is this a compressive or a tension force to know if the member is going to be able to sustain it. So the Fy's is going to tell us that FCD equals minus CY, meaning FCD equals minus 200 newtons, and that is in compression. Also because it's negative, right? Okay, and at pin A, the sum of the Fy's is going to give us an AY plus an FAB times 4/5 because of that angle. And therefore, FAB is going to equal minus 750 newtons, also in compression. Okay, questions? We can then turn to, so we basically visit each pin and do those same equations over and over again and find all the forces. Yeah, Isaac?
How are you finding numbers in numbers?
How are we finding numbers when there's no numbers given? There are numbers given. CX is the reaction force that we determined right over here.
Oh, okay, okay.
CY is the reaction force that we determined right over here.
So we already solved for C.
We already saw for some of them. We use them when we have them to fill in those.
So we use the things we solve when we're looking at the reaction force to solve for the reaction temperatures.
Yeah, we're looking at those reaction forces because those reaction forces are applied to the pins. And when we do the diagram of the pins, they show up on the diagram and they actually determine the other forces acting on that structure. Good question. Please keep asking questions. It looks really complicated, but it's just really kind of mechanical. It's very straightforward. At pin D, you can do the sum of the FX's. And that's going to give us 600 going to the right. And then minus FAD minus 3/5 FBD. Okay, 3/5 because FBD is going up and to the left. I'm going to have you guys do the last one. But we solved for FBC already, right? We got FBC over here. Wait, that's an FBD. Sorry about that. FBD. So we got an FAD and an FBD. And we got some of the FYs. That's going to be FCD going up and 4/5 of FBD. Well, we already found FCD. So the FY is going to tell us then that FBD is going to equal minus 5/4 times the minus 200 newtons that we found for FCD, right? And so therefore FBD is going to equal 250 newtons. And that is positive, meaning that it's in tension. And once we find FBD, we can plug that in and solve for FAD and find that FAD equals 450 newtons. Positive, so it also is in tension. So we found FBC, we found FCD, and we found FAB, we found FBD and FAD. We found all of the member forces already. There's still one more pin we haven't analyzed, and if you want to check, you can do the equations there and make sure that they also satisfy those, some of the fx is equal 0, some of the fy is equal 0. So this is a group thing. I want you all to throw out, I'm going to just say, Jose, give me an x component for the first equation. Some of the fx is equal 0, give me an x component. FPC. Matthew, give me another x component.
FBD times 3/5.
Yeah, 3/5 of FED. Daphne, your turn. Give me another x component. FAB times 4/5. Well, not 4/5 because the 3-4 triangle, 3-4-5 triangle has 3 on the horizontal part. So it's also going to be 3/5. And is it positive or negative? Okay, look at the arrow for FAB and tell me whether that's got a component that's going negative or positive in the horizontal direction. It's negative. Good. Okay, and the sum of the FYs, Isaac, give me a Y force. Good. David?
4/5.
Positive or negative? Okay, look at the arrow that FBD is drawn on, that free body diagram. And is the vertical component negative or positive on that arrow? Yeah, this is the arrow right here, right? The arrows, because we're stretching that member, right? So it's minus. Okay. And Elreza, one more. Another Y force, yeah. What's the missing force that we haven't done yet? FAB. Just FAB like that? Okay, times 4/5 is a positive or negative? Negative, good. Yeah, and that equals 0, and you can solve for those, and you plug in FAB, plug in all those things, and you should get 0 for all those as a check, right? And they'll check. Okay. So that is the thing in a nutshell. Now there's some other stuff here, which actually we sort of got another example here. This is on your handout too, right? Example 2.
Yeah.
Given P1 is 200, P2 is 500, we're going to find the forces in each member of the truss, analyze pin B and then pin C. This is a little simpler problem. So you saw a more complicated one. Some problems you don't have to find the reactions first. If you can find a joint that only has 2 unknowns, you can just go ahead and solve it right there. Which joint only has 2 unknowns on it? Well, if you look at this thing, what's going to be happening here at A, you're going to have an AY and an AX. Here you're going to have a CY. So at C, you've got sort of 3 unknowns, right? Those 2 members in the CY. But if you solve for CY, then you only have 2 unknowns, right? For A, you've got 4 unknowns. You got the 2 reaction forces and these 2 member forces, so you can't really start there. But B has 2 known forces and 2 unknown forces, so it's possible to start your analysis right there if you want to. So we can do at pin B, which got all drawn out for us, the sum of the Fx equals 0. So this is going to be at B. And that's going to be 500 plus, we got these 45-degree angles here. Let's see. Well, how do we know it's 45 degrees? Well, this guy is 45 degrees because this is 4 and that's 4. And this is 3, 4, 5 triangle again because of those sides. So 500 plus, what's an x component at B? FBC, cosine of 45, say, right? And then you got a negative x component minus FBA times 3/5. Yes? Why is FBC positive? Can you look at that arrow FBC here? And I'm talking about the x component, right? So if I take the x component of this FBC, isn't it going this way? And the y component is going that way? So that's why it's positive. Thank you for asking. The sum of the Fy's equals 0 is going to tell us that we've got a minus 200 and a minus FBC. And what's the multiplier on FBC? Sine of 45, right? FBC is going down. The vertical part's going down. And then we got what else? We got an FBA times what? 4/5. And it's minus 2, right? So you can solve these and find that FBA equals 214 positive, so that is tension, and FBC equals minus 525, and that is compression. There's still one more unknown. So they only asked us to find the forces in each member. We didn't ask to find the reactions. So you don't have to find the reactions if they don't ask for them. So the last unknown is FCA, and with the diagram here, the only thing that's going to give X forces is, the members. So you can do one equation here. So this is at pin C. You're going to have a minus FCA because it's pointing to the left, and you're going to have a now this is kind of interesting here. See, we saw in this diagram that FBC equals minus 525, meaning it's in compression. So that means if we had this drawn as a compressive force with the arrow going up and to the left, we have to put a minus sign there. That means the arrow flips around and goes down and to the right. You see that? The sign of that thing has flipped because of the negative sign here. This pulling has turned that thing into a pushing force, compressive force acting on a pin. Again, it's totally okay if you want to keep drawing your forces as tension forces, but you would have to put a minus sign right there, because that's what you determine in this for the answer for the one above it, right? See that? That makes sense? Either way, you can see that you're going to get a positive X force, right? Because if the number was positive, you would have a negative X force, but now the number's negative, that means the force is really going the other way. It really looks like that. So you're going to say 525.3 times the cosine of 45 degrees. Solving for FCA, you end up getting that FCA equals 371 pounds, and it is in tension. Okay, question? We got it? So there's one more concept and then 2 quiz slides. It's 10-2, but if you can stick around for another couple minutes, we can get through this really fast. The concept is that in certain trusses, depending on the loading, you'll get certain members that don't have any forces on them at all. And they're called zero force members. And inspection, by just looking at the structure, you can sort of determine which ones are zero force members. And what you do is you look for collinear members that have no applied loads. Collinear means 2 members that are connected in a line. So they make a line. And if there's no applied loads there, then those have to be, there could be a zero force member at that point. So looking at the structure here, member G, pin G, which has these 3 forces acting on it, these 2 being collinear, okay, means that if the sum of the Fy's equals 0, well, there's only one force that's in the Y direction. You see that? If you're doing the sum of the Fy's at G equals 0, and you only got one force in the Y direction, doesn't that force have to be 0? So that becomes a zero force member. You just sort of ignore, you don't ignore it, but it's just 0. Okay? And then you can look at pin D, and if you tilt your X and Y axes, again, you can see that if your X is going down along the FDF line, then the FDF has to be 0 as well, because these forces aren't going to be able to, if this is your Y-axis, these forces aren't orthogonal. They're not going to be able to do anything there. So also FDF happens to be 0. So that goes away. Whoops. And then, you wouldn't normally think of F as being a 0, or this, have a bunch of 0 forces there, but because that's 0, and you have these two collinear forces again, then FC has to be 0 as well. And this can kind of help simplify our analysis. If you can see what a 0 force member is, it'll sort of reduce the number of unknowns rapidly. It's not a huge thing. Usually there aren't any 0 force members, but sometimes you'll see, sometimes the way the structures are actually designed, they'll have some stuff in there that's just, there's no load on it. You can just ignore that stuff. It makes the analysis go a lot faster if you can see that. Isaac?
So, like, from a physical perspective, if you, like, remove those beams from that,
Yeah.
would the structure fail?
Great question, right? Yeah, so if you pull out the 0 force members, would the structure fail? No. You could just cut those members and it would still hold the load just fine.
It would hold the load exactly.
Well, now that I say that, the thing I worry about is, what if these forces are in compression? They'd be pushing at that pin, and it would probably buckle real easily if those 0 force members weren't there. They might be stabilizing a joint with a small amount of force. Yeah. Yeah, that's a good question, and I'm not a structural engineer, but mathematically it would be supported just fine. But realistically, there may be some issues when you do that. And then, it's 0 force member with this loading configuration, but if you actually hang a load like I here at F, then these are no longer 0 force members, right? Now they've got to actually take some load in. If you put a load here at G, then this guy can't be a 0 force member either, right? So if the loading changes, then the 0 force members change. Okay, so just to play around with these ideas, here's a conceptual question. Again, this is a really good reasoning question. If you're changing the truss by decreasing its height, so here you have the same load, the width is the same, the load P is the same, but you've changed the height by decreasing it to something like that. Which one of the following statements is true for the revised truss as compared to the original truss? The force in all its members have decreased, increased, remained the same, or none of the above? Isaac?
How is changing H affect changing the...
That's the question. Is it going to make the forces go up if you reduce the height? Think about it in a more extreme case where they're really almost flat. But you have the same P here. You change the length, sorry?
Did you change the length of H to the length of BA also?
BA, yeah. Yeah, so this is A now. So the members are getting shorter, but are the forces going up, down, or staying the same? Sorry? They're increasing. Why?
Because the angles are like fading, so getting closer to like...
Yeah, if you do the free body diagram, right? If you do the free body diagram at A, right? If you look at A on these two scenarios where you got this force, and let's assume they're in compression, so, and if they're at a relatively steep angle, right? You know that the vertical components of each of these forces has to add up to, in total, the force P, right? See what I'm saying? But if the angle has changed and it's more like, this, you've got to, if the angle's like that, you've got to have a much longer force line to get the same vertical component to kind of double up, right, with those forces, right? So the forces are going to have to now look something like that. Graphically, you can kind of see that the forces have to get bigger so that the y components add up to the same amount. Because the angle's so shallow, the forces have to get bigger to accumulate the same amount of y force. That makes sense? Could be on the final exam. Got to make sure you reason that. And then, how many zero force members are there in this truss? Which one is it? This one? This one?
Bottom two.
The bottom two?
Yeah.
I don't know. But remember, if you're trying to sum all the forces here, the vertical force can't be balanced by anything else, right? You know, if there's a force here, it's going to be balanced by an equal and opposite force here, right? But if there's a vertical force, who's going to balance it? There's no downward force there, right? So that vertical force has to be zero. That's a zero force member right there. Okay, call this pin C. Look at the forces at pin C, if they're all in tension, right? If you do the sum of if you call this FB or something, this is BA, or CA, sorry. If this is A, that's C. Sum of the FYs, tell me all the forces that are giving you a Y direction. Just FCA, right? And there's no other Y force, so it has to be zero. Right? Yeah, we do. But this pin has 5 members on it. And that vertical force is going to have to be sustained by these guys. No, these are forces. Right? The forces in those numbers to kind of do the vertical, they have to balance out the vertical part of that F load. But that F load doesn't transmit down to here. There's no other load applied at C. There's no vertical load applied to C, so that force of the member has to be zero because there's nothing to balance out anything else there.
How is that possible that you have a force at A that's connected to C, but C doesn't have it?
Because these members, call this B and D, remember, FBA and FDA are able to counteract the force, so there doesn't need to be a force in member AC.
Why is it that
Why is it that those members take the force and not AC? Because they can, and because AC cannot. Again, think about it. Suppose we found out that FCA was, say, 200 or negative 200, like it's in compression, right? Now, David, I want you to tell me how we can get the sum of the FYs equal to 0 at point C if FCA equals minus 200. What else is there to give you the opposite of that? At point C, there's nothing to give you a vertical force to balance that out. Do you agree? There's nothing else in the equation. The equation only has one term. The equation has to add up to 0. That one term, therefore, must be 0.
the support and the roller on like those
Has nothing to do with that. Just look at the pin. Look at this thing. There's no vertical force besides FCA. There's only one term. It has to be 0 for equilibrium. If it's not 0, the thing's going to move. Right? Isaac.
So because you have those diagonal lines,
Yeah.
which have both vertical and horizontal components, they can take
Yeah. The diagonal lines can handle vertical and horizontal forces.
yeah, so if it's like reverse and there's like a X and there's like 0 and the diagonal lines would take that.
I'm not able to parse your question because it's a little too complicated right now and it's late. But we can talk about it tomorrow. But there are two more zero force members in here. Can you see where they are?
The top one.
Yeah, this left top corner, right? If you do the diagram of the forces there, suppose they're all in tension, right? If this force is not 0, suppose this is 5, what's going to keep that pin from sliding to the right? Nothing. So the force has to be 0. What's going to keep the pin sliding down if there's a 5 Newton force there? Nothing. Then it's going to slide down. Well, if it's not sliding down, then it has to be 0 if it's in equilibrium, right? See it? That's the reason behind it. So there's 3 zero force members. This one, that one, and that one. Isaac.
Can you only have zero force members when you look at it from the pin?
Can you only have zero force members when you look at it from the pin? No, I mean, anything. The view of the pins is going to give you the same answer as if you do the view from the members. It's just easier for us to analyze.
Yeah, because I was thinking about how much we did last week, or there's some way when I did this connection.
Yeah, you may get zero forces at any time. There's another example here, but more importantly, the attention quiz. If you find that FBC equals minus 500 newtons, then member BC must be in what? Sorry? Compression. Right? Because the force is drawn pulling on the pin. That means the pin is pulling on the member, stretching it out. So it's tension. For the same magnitude of force to be carried, truss members in compression are generally made what as compared to members in tension? This is going to help your design project if you do one. Bigger. Because they can't handle compressive loads as well as tension loads. Tension load is like a cable, the fibers of wood and whatever steel, they actually usually work really well holding those forces in tension. But when you start compressing it, they buckle. And the thing bends at a lower force than the same force of tension. Okay? Hope you found that helpful. So we agreed then that we would do the second lecture online tonight, otherwise you weren't here. And then tomorrow we come in and we do the in-class problems. Tomorrow's Wednesday. And then we have another problem session on Thursday.
Are you going to post the lecture to look at the announcements? Or?
Yeah, I'll post it just to make sure everybody knows. Yep.